Have you ever wished you had a cheat code for reality? You know, a way to just bend the rules that we all take for granted? Well, it turns out the universe already has one built right in. And it's this cheat code that lets us do incredible things, like see the very building blocks of matter. Today, we're going to dive into how it all works.
So in our everyday world, some rules seem totally non-negotiable, right? You run into a wall, you stop. End of story. But here's the thing. When you zoom way, way down to the quantum level, the world of atoms and electrons, the rules get weird. A wall isn't a hard stop anymore. It's more like a probability puzzle. Getting through isn't impossible. It's just really, really, really unlikely.
Okay, so if the quantum world is this fuzzy place of probabilities, how does that help us in the real world? How in the world can we harness a bizarre rule like that to actually see, and get this, even move individual atoms? Well, that is the exact mystery we are about to solve.
The answer has this perfectly sci-fi sounding name, the quantum tunneling effect. This is the secret that basically unlocks what should be impossible and turns solid barriers into mere suggestions.
So what is it exactly? Well, think of it this way. In normal physics, if you don't have enough energy to push a boulder over a hill, you're stuck. Simple. But quantum particles, they also act like waves. And this wave-like nature means there's a small but very real chance that the particle can just appear on the other side of the hill without ever going over it. It doesn't smash through it, it just tunnels.
And this is the key to why it works. If you have an infinitely thick wall, that particle's probability wave just slams into it and fizzles out completely. Game over. Zero chance of transmission. But with a wall that has a finite thickness, something amazing happens. The wave starts to fade inside the wall, sure, but before it can fade away to zero, it reaches the other side. A tiny little piece of that wave survives, and that's all you need for the particle to have a chance to pop into existence over there.
All right, so if particles can do this, can they just tunnel through anything they want? Not quite. There are rules to this game, and understanding these rules is how we figured out how to use this incredible power.
And it all comes down to three things that honestly make a lot of sense. First, the barrier's width. Obviously, a thinner wall is going to be easier to tunnel through. Second, the barrier's height. A lower energy hill is easier to get past. And third, the particle's own energy. The more juice it has, the better its odds. It's still not enough energy to go over the barrier, but it definitely makes tunneling through it more likely.
Now here is where it gets really, really interesting. This relationship is not one-to-one. It's what we call exponential. As the source material says so well, even the tiniest changes to the barrier can create absolutely massive changes in the outcome.
Just how massive are we talking? We'll get a load of this number, 210%.
So what does that even mean? It means that if you change the width of that barrier by the absolute tiniest amount you can imagine, we're talking the size of a single hydrogen atom, the flow of particles tunneling through can more than triple. That sensitivity is almost unbelievable, and it's the very feature that we've learned to exploit.
And that brings us to one of the most incredible technologies ever invented, something that exists entirely because of that extreme sensitivity, the Scanning Tunneling Microscope, or STM for short. Okay, here's how it works. You take this ridiculously sharp needle and you bring it insanely close to a surface, just a few atoms away. That tiny gap of empty space between the tip and the surface, that's your quantum barrier. Then you apply a little voltage and boom, electrons start tunneling across that gap, which creates a tiny electrical current. And because that current changes so dramatically with even the slightest change in distance, you can use it to draw a perfect map of the surface atom by atom.
And this isn't just theory. This is the amazing payoff. In 1989, scientists used an STM to do something straight out of science fiction. They didn't just see atoms, they used the tip of the microscope to gently nudge individual xenon atoms into place, spelling out their company's logo. Think about that. They wrote a word using atoms as the ink.
But what might be even crazier is that this whole quantum cheat code isn't a clever trick that we humans invented. Nope, we just copied nature. The universe has been using this exact principle since the beginning of time.
For example, let's look at something called alpha decay. This is how really heavy, unstable atoms, like uranium, eventually calm down and become more stable. They do it by spitting out a little particle made of 2 protons and 2 neutrons. And the only reason they can do this at all is quantum tunneling.
So just picture this.
You've got this little particle trapped inside a nucleus, held in by the strong nuclear force, literally the strongest glue in the universe. It's bouncing around, wanting out, but it keeps slamming into this huge energy barrier. Classically speaking, it's in jail for life. It's never getting out. But its wave-like nature means its probability field kind of leaks through that barrier. And eventually, poof, it tunnels out. It's free, and the atom is just decayed.
And just like with the microscope, the sensitivity here is just staggering. I mean, look at this. A pretty small increase in the energy of that escaping particle, just the factor of 3, can make it 100 billion trillion times more likely to escape. That's a 1 with 20 zeros after it. This insane exponential rule is why some elements have half-lives of billions of years, while others are gone in a fraction of a second.
So, after all this weirdness, from microscopes that see atoms to particles breaking out of their own nucleus, let's just step back for a second. Why does any of this really matter? Well, here's the big picture. The universe, at its very core, doesn't run on the certainties that we're used to. It runs on probabilities. This means particles can and do show up in places that our everyday logic says are completely forbidden. And this isn't some quirky abstract theory. It's the fundamental cheat code behind both the technology we build and the natural processes, like radioactivity, that make the universe tick. The solid, predictable reality we think we know is actually built on a foundation of pure quantum strangeness.
So I'll just leave you with this question. If the solid reality that we all touch and see is ultimately governed by these bizarre, counterintuitive probabilities, it really makes you wonder, doesn't it? What else that we all think is completely impossible might just be extremely unlikely, waiting for just the right conditions to tunnel its way into existence.